text-to-speech synthesis is the artificial production of human speech. A computer system used for this purpose is called a speech computer or speech synthesizer, and can be implemented in software or hardware products. A text-to-speech system converts normal language text into speech. Other systems render symbolic linguistic representations like phonetic transcriptions into speech. Synthesized speech can be created by concatenating pieces of recorded speech that are stored in a database. Systems differ in the size of the stored speech units. A system that stores phones or diphones provides the largest output range, but may lack clarity. For specific usage domains, the storage of entire words or sentences allows for high-quality output. Alternatively, a synthesizer can incorporate a model of the vocal tract and other human voice characteristics to create a completely synthetic voice output. The quality of a speech synthesizer is judged by its similarity to the human voice and by its ability to be understood clearly. An intelligible text-to-speech program allows people with visual impairments or reading disabilities to listen to written works on a home computer. Many computer operating systems have included speech synthesizers since the early 1990s. A text-to-speech system is composed of two parts, a front end and a back end. The front end has two major tasks. First, it converts raw text containing symbols like numbers and abbreviations into the equivalent of written-out words. This process is often called text normalization, pre-processing, or tokenization. The front end then assigns phonetic transcriptions to each word, and divides and marks the text into prosodic units, like phrases, clauses, and sentences. The process of assigning phonetic transcriptions to words is called text-to-phoneme or grapheme-to-phoneme conversion. Phonetic transcriptions and prosody information together make up the symbolic linguistic representation that is output by the front end. The back end, often referred to as the synthesizer, then converts the symbolic linguistic representation into sound. In certain systems, this part includes the computation of the target prosody, which is then imposed on the output speech. History: long before electronic signal processing was invented, there were those who tried to build machines to create human speech. Some early legends of the existence of brazen heads involved Pope Sylvester II, Albertus Magnus, and Roger Bacon. In 1779, the Danish scientist Christian Kratzenstein, working at the Russian Academy of Sciences, built models of the human vocal tract that could produce the 5 long vowel sounds. This was followed by the bellows-operated acoustic mechanical speech machine by Wolfgang von Kempelen of Pressburg, Hungary, described in a 1791 paper. This machine added models of the tongue and lips, enabling it to produce consonants as well as vowels. In 1837, Charles Wheatstone produced a speaking machine based on von Kempelen's design, and in 1857, M. Faber built the Euphonia. Wheatstone's design was resurrected in 1923 by Paget. In the 1930s, Bell Labs developed the Vocoder, which automatically analyzed speech into its fundamental tone and resonances. From his work on the Vocoder, Homer Dudley developed a keyboard-operated voice synthesizer called the Vocoder, which he exhibited at the 1939 New York World's Fair. The pattern playback was built by Dr. Franklin S. Cooper and his colleagues at Haskins Laboratories in the late 1940s and completed in 1950. There were several different versions of this hardware device, but only one currently survives. The machine converts pictures of the acoustic patterns of speech in the form of a spectrogram back into sound. Using this device, Alvin Liberman and colleagues were able to discover acoustic cues for the perception of phonetic segments. Dominant systems in the 1980s and 1990s were the MyTalk system, based largely on the work of Dennis Klitt at MIT, and the Bell Labs system. The latter was one of the first multilingual language-independent systems, making extensive use of natural language processing methods. Early electronic speech synthesizers sounded robotic and were often barely intelligible. The quality of synthesized speech has steadily improved, but output from contemporary speech synthesis systems is still clearly distinguishable from actual human speech. As the cost-performance ratio causes speech synthesizers to become cheaper and more accessible to the people, more people will benefit from the use of text-to-speech programs. Electronic devices equals. The first computer-based speech synthesis systems were created in the late 1950s. The first General English text-to-speech system was developed by Noriko Umeda al. in 1968 at the Electrotechnical Laboratory, Japan. In 1961, physicist John Larry Kelly, Jr. and colleague Lou Eastman used an IBM 704 computer to synthesize speech, an event among the most prominent in the history of Bell Labs. Kelly's voice recorder synthesizer recreated the song Daisy Bell, with musical accompaniment from Max Matthews. Coincidentally, Arthur C. Clarke was visiting his friend and colleague John Pierce at the Bell Labs Murray Hill facility. Clarke was so impressed by the demonstration that he used it in the climactic scene of his screenplay for his novel 2001, A Space Odyssey, where the HAL 9000 computer sings the same song as it is being put to sleep by astronaut Dave Bowman. Despite the success of purely electronic speech synthesis, research is still being conducted into mechanical speech synthesizers. Handheld electronics featuring speech synthesis began emerging in the 1970s. One of the first was the Tilly & Systems Incorporated. Speech Plus portable calculator for the blind in 1976. Other devices were produced primarily for educational purposes, such as Speak and Spell, produced by Texas Instruments in 1978. Fidelity released a speaking version of its electronic chess computer in 1979. The first video game to feature speech synthesis was the 1980 shoot-'em-up arcade game, Stratovox, from Sun Electronics. Another early example was the arcade version of Berserk, released that same year. The first multiplayer electronic game using voice synthesis was Milton from Milton Bradley Company, which produced the device in 1980. Synthesizer Technologies. The most important qualities of a speech synthesis system are naturalness and intelligibility. Naturalness describes how closely the output sounds like human speech, while intelligibility is the ease with which the output is understood. The ideal speech synthesizer is both natural and intelligible. Speech synthesis systems usually try to maximize both characteristics. The two primary technologies generating synthetic speech waveforms are concatenative synthesis and formant synthesis. Each technology has strengths and weaknesses, and the intended uses of a synthesis system will typically determine which approach is used. Concatenation synthesis equals. Concatenative synthesis is based on the concatenation of segments of recorded speech. Generally, concatenative synthesis produces the most natural-sounding synthesized speech. However, differences between natural variations in speech and the nature of the automated techniques for segmenting the waveforms sometimes result in audible glitches in the output. There are three main subtypes of concatenative syntheses. Unit selection synthesis. Unit selection synthesis uses large databases of recorded speech. During database creation, each recorded utterance is segmented into some or all of the following: individual phones, diphones, half phones, syllables, morphemes, words, phrases, and sentences. Typically, the division into segments is done using a specially modified speech recognizer set to a forced alignment mode with some manual correction afterward, using visual representations such as the waveform and spectrogram. An index of the units in the speech database is then created based on the segmentation and acoustic parameters like the fundamental frequency, duration, position in the syllable, and neighboring phones. At runtime, the desired target utterance is created by determining the best chain of candidate units from the database. This process is typically achieved using a specially weighted decision tree. Unit selection provides the greatest naturalness, because it applies only a small amount of digital signal processing to the recorded speech. DSP often makes recorded speech sound less natural, although some systems use a small amount of signal processing at the point of concatenation to smooth the waveform. The output from the best unit selection systems is often indistinguishable from real human voices, especially in contexts for which the TTS system has been tuned. However, maximum naturalness typically require unit selection speech databases to be very large, in some systems ranging into the gigabytes of recorded data, representing dozens of hours of speech. Also, unit selection algorithms have been known to select segments from a place that results in less than ideal synthesis even when a better choice exists in the database. Recently, researchers have proposed various automated methods to detect unnatural segments in unit selection speech synthesis systems. Diphone synthesis. Diphone synthesis uses a minimal speech database containing all the diphones occurring in a language. The number of diphones depends on the phonotactics of the language. For example, Spanish has about 800 diphones, and German about 2,500. In diphone synthesis, only one example of each diphone is contained in the speech database. At runtime, the target prosody of a sentence is superimposed on these minimal units by means of digital signal processing techniques such as linear predictive coding, PASOLA or MBOLA. Or more recent techniques such as pitch modification in the source domain using discrete cosine transform. Diphone synthesis suffers from the sonic glitches of concatenative synthesis and the robotic-sounding nature of formant synthesis, and has few of the advantages of either approach other than small size. As such, its use in commercial applications is declining, although it continues to be used in research because there are a number of freely available software implementations. Domain-specific synthesis. Domain-specific synthesis concatenates pre-recorded words and phrases to create complete utterances. It is used in applications where the variety of texts the system will output is limited to a particular domain, like transit schedule announcements or weather reports. The technology is very simple to implement, and has been in commercial use for a long time, in devices like talking clocks and calculators. The level of naturalness of these systems can be very high because the variety of sentence types is limited, and they closely match the prosody and intonation of the original recordings. Because these systems are limited by the words and phrases in their databases, they are not general purpose and can only synthesize the combinations of words and phrases with which they have been pre-programmed. The blending of words within naturally spoken language, however, can still cause problems unless the many variations are taken into account. For example, in non-rhotic dialects of English the R in words like clear is usually only pronounced when the following word has a vowel as its first letter. Likewise in French, many final consonants become no longer silent if followed by a word that begins with a vowel, an effect called liaison. This alternation cannot be reproduced by a simple word concatenation system, which would require additional complexity to be context-sensitive. Formant synthesis Formant synthesis does not use human speech samples at runtime. Instead, the synthesized speech outputs is created using additive synthesis and an acoustic model. Parameters such as fundamental frequency, voicing, and noise levels are varied over time to create a waveform of artificial speech. This method is sometimes called rules-based synthesis. However, many concatenative systems also have rules-based components. Many systems based on Formant synthesis technology generate artificial, robotic-sounding speech that would never be mistaken for human speech. However, maximum naturalness is not always the goal of a speech synthesis system, and Formant synthesis systems have advantages over concatenative systems. Formant synthesized speech can be reliably intelligible, even at very high speeds, avoiding the acoustic glitches that commonly plague concatenative systems. High-speed synthesized speech is used by the visually impaired to quickly navigate computers using a screen reader. Formant synthesizers are usually smaller programs than concatenative systems because they do not have a database of speech samples. They can therefore be used in embedded systems, where memory and microprocessor power are especially limited. Because Formant-based systems have complete control of all aspects of the output speech, a wide variety of prosodies and intonations can be output, conveying not just questions and statements, but a variety of emotions and tones of voice. Examples of non-real-time but highly accurate intonation control in Formant synthesis include the work done in the late 1970s for the Texas Instruments toy Speak and Spell, and in the early 1980s Sega arcade machines and in many Atari, incorporated arcade games using the TMS 5220 LPC chips. Creating proper intonation for these projects was painstaking, and the results have yet to be matched by real-time text-to-speech interfaces. Articulatory synthesis Articulatory synthesis refers to computational techniques for synthesizing speech based on models of the human vocal tract and the articulation processes occurring there. The first articulatory synthesizer regularly used for laboratory experiments was developed at Haskins Laboratories in the mid-1970s by Philip Rubin, Tom Baer, and Paul Mermelstein. This synthesizer, known as ASY, was based on vocal tract models developed at Bell Laboratories in the 1960s and 1970s by Paul Mermelstein, Cecil Coker, and colleagues. Until recently, articulatory synthesis models have not been incorporated into commercial speech synthesis systems. A notable exception is the Next-based system originally developed and marketed by Trillium Sound Research, a spin-off company of the University of Calgary, where much of the original research was conducted. Following the demise of the various incarnations of Next, the Trillium software was published under the GNU General Public License, with work continuing as GNU Speech. The system, first marketed in 1994, provides full articulatory-based text-to-speech conversion using a waveguide or transmission line analog of the human oral and nasal tracts controlled by Cara Copyright's distinctive region model. More recent synthesizers, developed by Jean Schoentgen, Jorge C. Lucero and colleagues, incorporate models of vocal fold biomechanics, glottal aerodynamics and acoustic wave propagation in the bronchi, trachea, nasal and oral cavities, and thus constitute full systems of physics-based speech simulation. Hum-based synthesis Hum-based synthesis is a synthesis method based on hidden Markov models, also called statistical parametric synthesis. In this system, the frequency spectrum, fundamental frequency, and duration of speech are modeled simultaneously by hums. Speech waveforms are generated from hums themselves based on the maximum likelihood criterion. Sine wave synthesis Sine wave synthesis is a technique for synthesizing speech by replacing the formants with pure tone whistles. Challenges text normalization challenges The process of normalizing text is rarely straightforward. Texts are full of heteronyms, numbers, and abbreviations that all require expansion into a phonetic representation. There are many spellings in English which are pronounced differently based on context. For example, my latest problem is to learn how to better project my voice contains two pronunciations of project. Most text-to-speech systems do not generate semantic representations of their input texts, as processes for doing so are unreliable, poorly understood, and computationally ineffective. As a result, various heuristic techniques are used to guess the proper way to disambiguate homographs, like examining neighboring words and using statistics about frequency of occurrence. Recently TTS systems have begun to use hums to generate parts of speech to aid in disambiguating homographs. This technique is quite successful for many cases such as whether read should be pronounced as read implying past tense, or as read implying present tense. Typical error rates when using hums in this fashion are usually below 5%. These techniques also work well for most European languages, although access to required training corpora is frequently difficult in these languages. Deciding how to convert numbers is another problem that TTS systems have to address. It is a simple programming challenge to convert a number into words, like 1325 becoming 1325. However, numbers occur in many different contexts. 1325 inches may also be read as 1325, 1325, or 1325. A TTS system can often infer how to expand a number based on surrounding words, numbers, and punctuation, and sometimes the system provides a way to specify the context if it is ambiguous. Roman numerals can also be read differently depending on context. For example, Henry VIII reads as Henry VIII, while Chapter 8 reads as Chapter 8. Similarly, abbreviations can be ambiguous. For example, the abbreviation in for inches must be differentiated from the word in, and the address 12 St. John's Street uses the same abbreviation for both St. and Street. TTS systems with intelligent front ends can make educated guesses about ambiguous abbreviations, while others provide the same result in all cases, resulting in nonsensical outputs, such as cooperation being rendered as company operation. Text-to-phoneme challenges Speech synthesis systems use two basic approaches to determine the pronunciation of a word based on its spelling, a process which is often called text-to-phoneme or grapheme-to-phoneme conversion. The simplest approach to text-to-phoneme conversion is the dictionary-based approach, where a large dictionary containing all the words of a language and their correct pronunciations is stored by the program. Determining the correct pronunciation of each word is a matter of looking up each word in the dictionary and replacing the spelling with the pronunciation specified in the dictionary. The other approach is rule-based, in which pronunciation rules are applied to words to determine their pronunciations based on their spellings. This is similar to the sounding out, or synthetic phonics, approach to learning reading. Each approach has advantages and drawbacks. The dictionary-based approach is quick and accurate, but completely fails if it is given a word which is not in its dictionary. As dictionary size grows, so too does the memory space requirements of the synthesis system. On the other hand, the rule-based approach works on any input, but the complexity of the rules grows substantially as the system takes into account irregular spellings or pronunciations. As a result, nearly all speech synthesis systems use a combination of these approaches. Languages with a phonemic orthography have a very regular writing system, and the prediction of the pronunciation of words based on their spellings is quite successful. Speech synthesis systems for such languages often use the rule-based method extensively, resorting to dictionaries only for those few words, like foreign names and borrowings, whose pronunciations are not obvious from their spellings. On the other hand, speech synthesis systems for languages like English, which have extremely irregular spelling systems, are more likely to rely on dictionaries, and to use rule-based methods only for unusual words, or words that aren't in their dictionaries. Evaluation challenges The consistent evaluation of speech synthesis systems may be difficult because of a lack of universally agreed objective evaluation criteria. Different organizations often use different speech data. The quality of speech synthesis systems also depends to a large degree on the quality of the production technique and on the facilities used to replay the speech. Evaluating speech synthesis systems has therefore often been compromised by differences between production techniques and replay facilities. Since 2005, however, some researchers have started to evaluate speech synthesis systems using a common speech dataset. Prosodics and emotional content A study in the journal Speech Communication by Amy Drahota and colleagues at the University of Portsmouth, UK, reported that listeners to voice recordings could determine, at better than chance levels, whether or not the speaker was smiling. It was suggested that identification of the vocal features that signal emotional content may be used to help make synthesized speech sound more natural. One of the related issues is modification of the pitch contour of the sentence, depending upon whether it is an affirmative, interrogative or exclamatory sentence. One of the techniques for pitch modification uses discrete cosine transform in the source domain. Such pitch-synchronous pitch modification techniques need a priori pitch marking of the synthesis speech database using techniques such as epoch extraction using dynamic Plosian index applied on the integrated linear prediction residual of the voiced regions of speech. Dedicated hardware, early technology, icophone, Votracks, SCO1A, SCO2/SSI263/Artic 263. General Instrument SPO256AL2, National Semiconductor DT1050 Digitalker, Silicon Systems SSI263, Texas Instruments LPC Speech Chips, TMS5110A, TMS5200, MSP50C620, sold to Sensory, Incorporated in 2001. Current, Magnavation SpeakJet TTS256 Hobby and Experimenter. Epson S1V30120F01A100 IC Talk-based voice, robotic, Eng Spanish, text-speak TTS-MICs, modules and industrial enclosures in 24 languages. Human-sounding, phoneme-based. Hardware and software systems, popular systems offering speech synthesis as a built-in capability. Mattel the Mattel Intellivision game console, which is a computer that lacks a keyboard, offered the IntelliVoice voice synthesis module in 1982. It included the SPO256 narrator speech synthesizer chip on a removable cartridge. The narrator had 2 kilobytes of read-only memory, and this was utilized to store a database of generic words that could be combined to make phrases in Intellivision games. Since the orator chip could also accept speech data from external memory, any additional words or phrases needed could be stored inside the cartridge itself. The data consisted of strings of analog filter coefficients to modify the behavior of the chip's synthetic vocal tract model, rather than simple digitized samples. SAM also released in 1982, Software Automatic Mouth was the first commercial all-software voice synthesis program. It was later used as the basis for Macintalk. The program was available for non-Macintosh Apple computers, various Atari models and the Commodore 64. The Apple version preferred additional hardware that contained DACs, although it could instead use the computer's 1-bit audio outputs if the card was not present. The Atari made use of the embedded POKEY audio chip. Speech playback on the Atari normally disabled interrupt requests and shut down the ANTIC chip during vocal output. The audible outputs is extremely distorted speech when the screen is on. The Commodore 64 made use of the 64's embedded SID audio chip. Atari arguably, the first speech system integrated into an operating system was the 1400XL/1450XL personal computers designed by Atari, incorporated using the Votrax SC01 chip in 1983. The 1400XL/1450XL computers used a finite-state machine to enable World English spelling text-to-speech synthesis. Unfortunately, the 1400XL/1450XL personal computers never shipped in quantity. The Atari Street computers were sold with speech TOS on floppy disk. Apple the first speech system integrated into an operating system that shipped in quantity was Apple Computer's Macintalk. The software was licensed from third-party developers Joseph Katz and Mark Barton and was featured during the 1984 introduction of the Macintosh computer. This January demo required 512 kilobytes of RAM memory. As a result, it could not run in the 128 kilobytes of RAM the first Mac actually shipped with. So, the demo was accomplished with a prototype 512K Mac, although those in attendance were not told of this, and the synthesis demo created considerable excitement for the Macintosh. In the early 1990s, Apple expanded its capabilities, offering system-wide text-to-speech support. With the introduction of faster power PC-based computers, they included higher quality voice sampling. Apple also introduced speech recognition into its systems, which provided a fluid command set. More recently, Apple has added sample-based voices. Starting as a curiosity, the speech system of Apple Macintosh has evolved into a fully supported program, Plain Talk, for people with vision problems. Voiceover was for the first time featured in Mac OS X Tiger. During 10.4 and first releases of 10.5, there was only one standard voice shipping with Mac OS X. Starting with 10.6, the user can choose out of a wide-range list of multiple voices. Voiceover voices feature the taking of realistic-sounding breaths between sentences, as well as improved clarity at high read rates over Plain Talk. Mac OS X also includes Say, a command-line-based application that converts text to audible speech. The Apple Script Standard Editions includes a Say verb that allows a script to use any of the installed voices and to control the pitch, speaking rate and modulation of the spoken text. The Apple iOS operating system used on the iPhone, iPad and iPod Touch uses VoiceOver speech synthesis for accessibility. Some third-party applications also provide speech synthesis to facilitate navigating, reading web pages or translating text. Amiga OS The second operating system to feature advanced speech synthesis capabilities was Amiga OS, introduced in 1985. The voice synthesis was licensed by Commodore International from Soft Voice, Incorporated, who also developed the original Macintalk text-to-speech system. It featured a complete system of voice emulation for American English, with both male and female voices and stress indicator markers, made possible through the Amiga's audio chipset. The synthesis system was divided into a translator library which converted unrestricted English text into a standard set of phonetic codes and a narrator device which implemented a Formant model of speech generation. Amiga OS also featured a high-level speak handler, which allowed command line users to redirect text output to speech. Speech synthesis was occasionally used in third-party programs, particularly word processors and educational software. The synthesis software remained largely unchanged from the first Amiga OS release, and Commodore eventually removed speech synthesis support from Amiga OS 2.1 onward. Despite the American English phoneme limitation, an unofficial version with multilingual speech synthesis was developed. This made use of an enhanced version of the translator library which could translate a number of languages, given a set of rules for each language. Microsoft Windows equals. Modern Windows desktop systems can use SAP i4 and SAP i5 components to support speech synthesis and speech recognition. SAP i4.0 was available as an optional add-on for Windows 95 and Windows 98. Windows 2000 added Narrator, a text-to-Euro speech utility for people who have visual impairment. Third-party programs such as CoolSpeech, Text Aloud and UltraHal can perform various text-to-speech tasks such as reading text aloud from a specified website, email account, text document, the Windows clipboard, the user's keyboard typing, etc. Not all programs can use speech synthesis directly. Some programs can use plugins, extensions or add-ons to read text aloud. Third-party programs are available that can read text from the system clipboard. Microsoft Speech Server is a server-based package for voice synthesis and recognition. It is designed for network use with web applications and call centers. Text-to-speech systems. Text-to-speech refers to the ability of computers to read text aloud. A TTS engine converts written text to a phonemic representation, then converts the phonemic representation to waveforms that can be output as sound. TTS engines with different languages, dialects and specialized vocabularies are available through third-party publishers. Android version 1.6 of Android added support for speech synthesis. Internet currently, there are a number of applications, plugins and gadgets that can read messages directly from an email client and web pages from a web browser or Google toolbar, such as Text-to-Voice, which is an add-on to Firefox. Some specialized software can narrate RSS feeds. On one hand, online RSS narrators simplify information delivery by allowing users to listen to their favorite news sources and to convert them to podcasts. On the other hand, online RSS readers are available on almost any PC connected to the Internet. Users can download generated audio files to portable devices, for example with the help of podcast receiver, and listen to them while walking, jogging or commuting to work. A growing field in Internet-based TTS is web-based assistive technology, for example. Browsy Aloud from a UK company and Red Speaker. It can deliver TTS functionality to anyone with access to a web browser. The non-profit project PDAlphan was created in 2006 to provide a similar web-based TTS interface to the Wikipedia. Other work is being done in the context of the W3C through the W3C Audio Incubator Group with the involvement of the BBC and Google Incorporated. Open source systems that operate on free and open source software systems including Linux or various, and include open source programs such as the Festival Speech Synthesis System, which uses diphone-based synthesis, as well as more modern and better sounding techniques, eSpeak, which supports a broad range of languages, and GNU Speech, which uses articulatory synthesis from the Free Software Foundation. Others. Following the commercial failure of the hardware-based IntelliVoice, gaming developers sparingly used software synthesis in later games. A famous example is the introductory narration of Nintendo's Super Metroid game for the Super Nintendo Entertainment System. Earlier systems from Atari, such as the Atari 5200 and the Atari 2600, also had games utilizing software synthesis. Some e-book readers, such as the Amazon Kindle, Samsung E6, Pocketbook e-Reader Pro, Entourage Edge, and the BookBook Neo. The BBC Micro incorporated the Texas Instruments TMS 5220 speech synthesis chip. Some models of Texas Instruments home computers produced in 1979 and 1981 were capable of text-to-phoneme synthesis or reciting complete words and phrases, using a very popular speech synthesizer peripheral. TI used a proprietary codec to embed complete spoken phrases into applications, primarily video games. IBM's OS/2 Warp 4 included VoiceType, a precursor to IBM ViVoice. GPS navigation units produced by Garmin, Magellan, TomTom and others use speech synthesis for automobile navigation. Yamaha produced a music synthesizer in 1999, the Yamaha FS1, which included a Formant synthesis capability. Sequences of up to 512 individual vowel and consonant formants could be stored and replayed, allowing short vocal phrases to be synthesized. Speech synthesis markup languages. A number of markup languages have been established for the rendition of text-to-speech in an XML-compliant format. The most recent is Speech Synthesis Markup Language, which became a W3C recommendation in 2004. Older speech synthesis markup languages include Java Speech Markup Language and Sable. Although each of these was proposed as a standard, none of them have been widely adopted. Speech synthesis markup languages are distinguished from dialogue markup languages. Voice XML, for example, includes tags related to speech recognition, dialogue management and touch-tone dialing, in addition to text-to-speech markup. Applications. Speech synthesis has long been a vital assistive technology tool, and its application in this area is significant and widespread. It allows environmental barriers to be removed for people with a wide range of disabilities. The longest application has been in the use of screen readers for people with visual impairment, but text-to-speech systems are now commonly used by people with dyslexia and other reading difficulties, as well as by pre-literate children. They are also frequently employed to aid those with severe speech impairment, usually through a dedicated voice output communication aid. Speech synthesis techniques are also used in entertainment productions such as games and animations. In 2007, Anemo Limited announced the development of a software application package based on its speech synthesis software FineSpeech, explicitly geared towards customers in the entertainment industries, able to generate narration and lines of dialogue according to user specifications. The application reached maturity in 2008. When NEC Biglop announced a web service that allows users to create phrases from the voices of Code Geass, Lee Louch of the Rebellion, or 2 characters. In recent years, text-to-speech for disability and handicapped communication aids have become widely deployed in mass transit. Text-to-speech is also finding new applications outside the disability market. For example, speech synthesis, combined with speech recognition, allows for interaction with mobile devices via natural language processing interfaces. Text-to-speech is also used in second language acquisition. Voki, for instance, is an educational tool created by Oddcast that allows users to create their own talking avatar, using different accents. They can be emailed, embedded on websites or shared on social media. In addition, speech synthesis is a valuable computational aid for the analysis and assessment of speech disorders. A voice quality synthesizer, developed by Jorge C. Lucero al. at University of Brasilia, simulates the physics of phonation and includes models of vocal frequency jitter and tremor, airflow noise and laryngeal asymmetries. The synthesizer has been used to mimic the timbre of dysphonic speakers with controlled levels of roughness, breathiness and strain. APIs. Multiple companies offer TTS APIs to their customers to accelerate development of new applications utilizing TTS technology. Companies offering TTS APIs include AT&T, Ivona, Neospeech, RedSpeaker, Synvo and Yarkeep2Me. For mobile app development, Android operating system has been offering text-to-speech API for a long time. Most recently, with iOS 7, Apple started offering an API for text-to-speech. See also. References. External links, tool for speech synthesis in the browsers via Google Chrome, whole articles reader using speech synthesis via Google Chrome, text-to-speech synthesis in the web browser with JavaScript, speech synthesis at DMOZ, synthesis of disordered voices, at University of Brasilia. Text-to-voice or text-to-speech Firefox add-on, Dennis Klutz History of Speech Synthesis, verbose text-to-speech. Text-speak multilingual text-to-speech. Simulated singing with the singing robot Pavarotti or a description from the BBC on how the robot synthesized the singing. Klutz's last tapes, a BBC Radio 4 program on the history of speech synthesis with many examples of electronic speech included. Tamil and Kannada TTS demo by Medical Intelligence and Language Engineering Lab, Indian Institute of Science. What is text-to-speech and how does it work? A basic explanation of TTS and USS synthesis by Neospeech.